on to the next section of our text. We've been building up these solids of revolution, but we have only been using this idea as an example of calculating volume through integration, right? So here we have some sort of vase drawn along the x-axis, and we have already seen how to integrate and find the volume of such a shape. Now, there are other questions we could answer here using integrals. For example, what's the surface area of this shape? How much paint would it take to paint something like this? If I was trying to design an object out of plastic and I wanted to minimize how much I need to create the walls of this vessel, how could I actually calculate that surface area? So once again, I want to make an approximation by chopping this figure up into small pieces. And as I take more of those pieces, as those pieces get smaller, my approximation gets better. Okay. So here, at least the way this is drawn, we're rotating around the x-axis. We have some curve called f of x here shown in pink. We're rotating it around, we get this nice vase. Let's try to chop up the x-axis. As usual, we'll chop it into pieces of the same width everywhere. So we'll call those pieces, say they have width delta x. Give those endpoints names x0, x1, so on up to xn. And what we do here is sort of a cross between the arc length formula that I talked about yesterday and some of the volume ideas that I was talking about on Monday and Tuesday. Let's put it all together, see what we can do with this. In pink on this figure, we've highlighted a single band, let's call it, or a belt perhaps, that we'd like to find the surface area of, right? So we're just taking this pink line segment here and rotating it about the x-axis. Well, if I want to find the surface area of that, I will need to know the height of that band, and I will need to know the radius of that band. So here, the height is actually going to be the width here because it's on its side. The radius, well, the radius is just going to be the average of the two different y coordinates, like so. And now to actually find the length of that line segment is exactly what we did for the arc length formula. I recommend you go back and check on that video. But we do get the length is the square root of quantity 1 plus f prime of x squared. This x star here in the derivative is saying that it's just some number between the two different endpoints. That square root is multiplied by the width, which is delta x. It's always delta x, isn't it? Again, because we are using Pythagorean theorem. Okay. What does a single piece of surface area here look like? I've got 2 pi times my radius times that length. So I kind of squint a bit. I see 2 pi, the value of the function, evaluated at xi star, times the square root of 1 plus f prime of xi star squared, all delta x. This is still my approximation to the surface area. And this formula is the approximation of a single one of those bands. I am going to add them all up using my sigma operator here. The sigma just tells me it's a whole bunch of plus signs. Just add them all up. Now, that approximation gets better the more bands that I take. So let's take n to infinity, calculate the limit of this formula, and, well, what is a limit of Riemann sums? It's an integral. This gives me my surface area formula. To calculate the surface area of a surface of revolution between x coordinates a and b, we will integrate from a to b 2 pi f of x times the square root of 1 plus f prime of x squared, all dx. There we go.